think, oh, this is appropriate, but is there a segment that, any questions you may have, let us help you today, Monday, and not Thursday at 10 p.m. or something like that. Okay, we want to help you. We want to give you time to actually do the work. Okay. And okay, let's continue on anode materials. We'll wrap this up, and then we'll go on to life cycle assessment of fuel cells. We'll focus on polymer electrolyte membrane fuel cells first. We'll touch upon a little bit of solid oxide fuel cells, but there's some overlap there, so I won't be, repeating myself too much. And then we'll go on to critical elements. So we'll see if we'll get to critical elements by end of Wednesday lecture, probably more likely beginning of Friday's lecture. Critical elements of both materials and fuel cells, but also going into lithium-ion batteries. So we'll revisit those discussions there in regards to material sourcing and such. Okay, so we went in depth on solid electrolyte fuel cell electrolytes. Now we'll cover anode materials as well as cathode materials and processing and assembly of these cells themselves. Right. So reminder, what happens at the anode? H2 reacts with oxide, so O2 minus. Now the oxygen has come in as a fuel source. Sorry, the oxygen has come in. It's being split from O2, so that's oxygen in its zero valence state into now O2 minus. So it's been reduced, and now you're going to have the waste that comes out to H2 minus, right? So the reigning material, or the material that's most active and used as an anode material is, interestingly, nickel substituted zirconia. So you see now there's a theme that zirconia is a really huge player in the solid oxide fuel cell world. So, but it's not just, it's not just yttria with a sprinkling of nickel. It's what's called a cermet. So it's a ceramic material. So that's where the yttria stabilized zirconia. So that's a solid solution of Y2O3 and ZrO2. And then you sinter that with some nickel. So that's where the metal comes in. So that is referred to a cermet. And you sinter them. So you heat up, your mixture at high temperature. You make a composite out of that. You reduce the density, so it's not this, porous type material. But you can see, but you do need some sort of porosity because you need space for gases to actually flow. So there's a middle ground as to, you don't want the material to be too porous, but you also don't want it to be too dense where your fuel can't get through. So the attractive part about using yttria stabilized zirconia as part of your anode material structure is that now when you mix nickel, this nickel YSZ with the YSZ electrolyte itself, is that when you increase the temperature to 600, 800 C, the two materials are so similar that the thermal expansion differential is not going to be a significant factor in the degradation of your fuel cell itself. Because you can imagine if you have, let's say, a metal as an anode, and then a ceramic as an electrolyte, and then a metal again as a cathode material, you can imagine the thermal expansion at 600, 800 C. That is actually significant. And if you're making these thin films, you can imagine also that you're going to initiate cracking because they're heating at different rates. The lattice expansion is at different rate. So you're introducing a degradation in your fuel cell by the sheer fact that these materials are dissimilar, right? So if you're mixing in nickel YSZ into now YSZ as well, you're stabilizing that that sandwich mechanically. So what typically happens is you want some porosity, right, for the fuel to come in, but you don't want too much porosity because towards the current collector side, you actually want it to be dense so that you have an electrical connection. So what people typically do is they make what's called a graded structure. So they just changed the porosity. So you can deposit down if you make a slurry, say, your ceramic and some solvent. If you're spray coating or screen printing or what have you, you deposit down of some known porosity, you sinter under, your sintering conditions make it so that it's quite dense, and then it's less dense, and it's less dense. Okay. So the graded structure helps, for the fine porosity towards the electrolyte, and then coarser porosity towards the outer layer. Right. So some of the limitations, if you have nickel, and this is one of the reasons why in heterogeneous catalysis people avoid nickel, is because it has low tolerance to sulfur. So if for whatever reason you have some sulfur impurities, nickel sulfide tends to form, and then you don't have active site on nickel to do your catalysis. So anything where you reduce the triple phase boundary site. So this is, the electrolyte. These are the catalyst particles here. That these junctures that where the gas, the electrolyte, and the catalyst all meet, that is where the catalysis happens. That is where the ORR happens. That is where the H2 oxidation happens. If those sites go away, your catalyst will die. So, so it doesn't matter if you have, the most pristine octahedra that you synthesize, for nanostructure or whatever, what have you. As the fuel cell progresses, as as it's used in service, these nanostructured catalyst particles will actually evolve. And if you lose whatever you design, whatever facet you design in the beginning, your catalytic activity will decrease as well, because it is at these triple phase boundary sites that dictate and govern the performance of your fuel cells, right? So people, it's not that you need to strive for perfection in terms of I have to make 5 nanometer spheres, or I calculate I need cubes or whatever, I'm going to set out to make that, because as your catalyst evolves, that will change. But the advantage of starting off with uniform catalyst morphology and size is that then you can say, well, I started off with this and my degradation is at this rate. So I can then backtrack and say, well, if my structure is X, then I can say my, the electrochemical property, is you can quantitatively link the property to the structure. So there is advantage to doing that. But when you scale up from the lab scale, where you can make things as perfect as you want, when you scale up in your manufacturing, that's not so easy to do. So there's some fine balance of, it's good enough, it's uniform enough, we can move on. As long as the catalysts are stabilized under, whatever conditions, 600, 700, 800 C and X, whatever humidity and gas flow rate, blah, 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 then it's good enough, right? So.
Just like a basic question,
Yeah.
kind of looking at this, I was kind of confused about so at higher temperatures, the issue with these is that they're not stable.
Yeah.
Okay, that's what what's limiting the efficiency for these.
Yes.
Okay.
Oh, well, okay. I guess that's a general question. Okay. Actually, very specific. All right. Yes is my general answer to the general question, but it depends too. So if you are operating at higher temperatures, so some of the electrolytes that I discussed last time, right? At higher temperatures, depending on if you're the bismuth, bismuth oxide electrolyte, or the perovskite, there can be phase transformations that are not suitable for the ionic connectivity. There's a certain phase at high temperature that corresponds to high ionic conductivity phase. So if you operate out of that temperature regime, you won't have the high ionic conductivity phase. Once, if you have all these mixtures, right, your compound has this cocktail of stoichiometries, what tends to happen is you'll start to have decomposition, where you may stabilize the binary phase, where you have this complex ternary ceramic compound, or you have quaternary, or you have quinary. The more complex your compound becomes, with all these deviation, small changes in stoichiometry, that's fine. You can do a lot of engineering in terms of, okay, if I dope in this and I dope in this, your phase diagram becomes really complex, because what tends to happen is you add in more elements, you're going to start, the complexity of your phase diagram, chances are, but you're going to stabilize like the binary oxides as well. And the higher temperature you go, that's probably going to be what happened. And then they'll actually turn into these grains where they impede ionic connectivity, because ionic connectivity of the binary phase is just not that high, if conducting at all. So can you make like a bulk metallic glass kind of composition where you like sprinkle in everything, and like 20 elements later you have like the best highest strength bulk metallic glass? Well, sure, but then you have a slew of other problems as well, with phase decomposition. So that's one end to answer your question about going to higher temperatures. The other issue is you want to operate at lower temperatures as possible, right? You just don't want, if you don't have to heat your cell as high, then you have fewer problems of heat, like thermal management. So ideally, you want to go to lower temperatures, but then you have to offset kinetic, like slower kinetics. But how much can you live with? So you do those types of studies in terms of ionic connectivity as a function of temperature. And the other issue is this higher temperature phases that have higher ionic connectivity. If you want to bring them down, now you have to substitute to stabilize the high temperature phases at lower temperatures, like the yttriostabilized zirconia. So that is one strategy, but the but is, now we go back to my original argument, is you start doping in, you start making your phase diagrams more complex, and you start stabilizing decomposition phases. So welcome to engineering. Yep. But yeah, I mean, I should say, that's not to say that we shouldn't tackle these problems. These are just material science problems. They are not insurmountable. These problems are not insurmountable. It's just, these are all the things one has to consider when designing a material. That's it. They're constraints, so that's just engineering as a field. Okay, so for cathode material here, on the cathode side, you have O2 becoming reduced to O2 minus, right? So the ideal case is you have porosity. You have some porosity so that, once again, gases can flow. So you don't want to sinter material too much, right? And the material that is the dominant, oh, I just realized, I think I said anode was where O2 was reduced. It's hydrogen oxidation. Sorry, cathode is oxygen reduction. So the reigning material is strontium dope, lanthanum manganate. Interestingly enough, we're talking about high temperature lanthanum manganate, MnO3, but at low temperature, I'm talking like 10 Kelvin, 50 Kelvin, extremely low temperature. These materials are really interesting for the magnetism at low temperatures in this particular material. The magnetism being located on the manganese site makes it really interesting quantum information science material. So if you're thinking about quantum computing, things like that, very interesting material, but on the low temperature end. High temperature end, it's a great material for solid oxide fuel cell cathodes. So the ion conductivity is quite high, 100 Siemens per centimeter at 600. So that's typical operating temperature for solid oxide fuel cell. And as a cathode, you want the material to be electronically conducting as well, right? So here you're starting to see where the engineering comes in. The electrolyte, you want it to be ionically conducting, but electrically insulating, because you don't want to short your cell. You want to keep the cathode and the anode separate in terms of electrical conductivity. But with your electrode, you want high electronic conductivity, but you still need ionic conductivity because the O2 minus is still coming in. So the O2 minus still needs to conduct, but your cathode also needs to be electronically conductive because it's touching the current collector, and that current needs to be separated and going to your external circuit, generating electricity for your application. So engineering both electronic conductivity and ionic conductivity is what's called an MIEC. So you need something that conducts both. And that's not always so easy, right? Most ceramics are not electrically insulating, right? Metals are electronically conductive, but not really ionically conductive because they like to stay in the zero valence state. They like to stay as metal, right? So these type of materials have the sweet spot where they're ionically conductive, but they're also electronically conductive, right? So that's why this material has been sort of the reigning material for quite a long time. This and it's often referred to as LSM, but the stoichiometry is there, as you can see, and it's a perovskite type material. So as a reminder, these perovskite type materials, they tend to have the A site here, the B site is in the middle of that octahedron, and the oxygens make up the 8 vertices. So then you have, sorry, the 6 vertices, so you have 8 faces, which makes up an octahedron. So 4 on top, 4 on bottom, square pyramid, put them together, and you have an octahedron. So what have people done with them? Well, they've substituted with strontium to get p-type conductivity. So the conductivity here, you can see it increases to 290 Siemens per centimeter for the electronic conductivity at 1000 C. And so what you can do then is you actually mix this lanthanum strontium dope manganese oxide compound with a little bit of YSC. And so you get the ionic conductivity of YSC as well, and you get the electronic conductivity of LSM. And what people have also done is they've tried substituting in with iron as well. But what tends to happen is if you get higher ionic conductivity, you can see now you have 1, 2, 3, 4, 5 elements. And at high temperatures, what tends to happen is you get decomposition out of lanthanum zirconate, cobalt oxide, the binary phase, and a slew of other things, iron oxide as well. So you have phase segregation, decomposition. But interestingly enough, if you start adding in lithium to lanthanum zirconate, you get lithium lanthanum zirconate, which is LLZO, which is a very common solid electrolyte for lithium ion batteries for those interested in solid state, all solid cells. So, it's all related. Okay, so in terms of the assembly, so you've chosen your material based on, very fundamental rules of chemistry, like just will these two compounds mix together? Basic fundamental rules of material science. What does the phase diagram look like? What are the phases at high temperature? Well, and then you make your pellet, you measure the ionic conductivity, you say, great, these are the materials I'm going to go with. Now I need to start assembling them. This is where the hard part comes in. It can't be too thin. Each layer cannot be too thin because obviously cracking will occur, and then possibly shorting of your cell as well. So what typically happens is the 3 obvious approaches is, well, make them thin, start off with your electrolyte or your cathode or your anode, and then start depositing the other materials on. So the typical strategies are listed here. So first, you could work on your your electrolyte. And so here, this approach makes it really thick. You say, okay, I'm going to make the electrolyte thick. I'm going to prevent, the cathode and the anode from touching each other. That's great. And if you make it thick, you could see the electrolyte layer here is 200 to 500 microns thick. And the cathode and the anode are about 100 to 200 microns each. So the total is not that much. It's under a millimeter, right? So you can imagine if your electrolyte is about half or more in terms of thickness of your entire sandwich, then it becomes a structural component. It now has to be strong enough so that your entire assembly doesn't crack. So not only is it an electrochemical material, as in it's responsible for the ionic conductivity in your fuel cell, but it becomes a structural component. So that's something important to keep in mind. So what typically happens here is you make your electrolyte, you press it, you center it, and then you deposit, the cathode or the anode on. And then there are a number of ways you can do it. If you have the ceramic pellet now, or your thin film, say, you can dip coat it into solution, then dry out the solution, then heat it up, put it in the furnace, and then repeat for the other electrodes. So if you start off with the anode, then you heat it up. Then now you have your cathode, your anode and your electrolyte. Then you deposit the cathode on the other side. So you can do a number of things. You can spray coat, kind of like painting a car, that kind of thing. You can dip coat. So you have a little robot which does dipping. You can tape cast. You can screen print like you would a t-shirt, your slurry. So pretty simple type of techniques. So this type of assembly, what you're looking for is you don't want your eventual assembly to delaminate, right? You want them all to stick together. So you have a conduction pathway. And you also want to prevent thermal shock. So you want to anneal your composite together at high temperatures. So yes, vacation.
Process that's preferable that using metric speed.
That depends. So spray coating is pretty fast because you just need to make, your solution, you hook up a hose and you spray paint, but then you have a solvent problem. Because typically the ceramics, you disperse them in, let's say, alcohol, even ethanol, say, okay, that's great. But now once you spray, you have to evaporate off the ethanol. So you kind of need a little bit of gentle heat to get, to get that going. So you add like a step. Dip coating is slower, so that's not as preferred. Also, you need a huge volume of solvent that you also now need to dry off. So that's not as ideal either. So in terms of recycling the solvent, if you're evaporating it, maybe you can collect it somehow and then reuse it, but there's no guarantee that your solvent is 100% pure again, unless you do filtration. So, but dip coating is typically longer than just spray coating. Spray coating, you can achieve a larger area very quickly. Tape casting, easier, but you're limited by the area. So if you're making the fuel cells that I showed before from Bloom Energy and it's the size of your pump, tape casting that is no problem. But if you wanted to have larger size or faster assembly, spray coating is the way to go. But the limitation is your solvent. So and dealing with the solvent, yes. Oh, wait, what was the first thing you said? Yes. So the question is, well, can you sputter? The only problem there is, well, a potential problem, maybe it's not a problem, but something you have to consider for with sputtering is it is solventless, but you need a target. As in, the sputter, right? You need to have like whatever material you want to deposit. You hit your target comes down, right? It sputters, and your target comes down. So you need this target. The other issue, potential issue, now it's not always if you need to cover this area, but aerial, the area could be a limiting factor, right? Sputtering machines are not like gigantic like this, right? But they could potentially achieve more uniform thickness. So that is an advantage. But most sputterers, you have to evacuate the system. It can't be done in an ambient atmosphere. So while you avoid, let's say, higher costs of solvent, vats and vats of solvent, drying off the solvent, recycling the solvent potentially, you're limited by size, and you have to now evacuate the system. So the time that you have to wait for the chamber to pump down could be a problem, but you do get more uniform, which is why the photovoltaic community sometimes sputters, because that's what they need, right? They don't need always the fastest technique, they need the most uniform, or the technique that generates the most uniform of thin films. So it's a real trade-off. You know, but you choose the technique for, for what you need, all right. So the next two assemblies are different flavors of what I just talked about. So here the cathode comes on first. So here you put down the cathode. So you can see the cathode is now going to provide structural support. So it's going to be the thickest component. It's 1 to 2 millimeters. So then you put down your cathode material. Let's say it's LSM, strontium dope, lanthanum manganate. You mix it with binder and pore former. So what that means is you mix in a little bit of polymers to hold all your ceramic material together. So now you have a composite. And you also want some sacrificial polymer. So if you mix in a little bit of polymer of the right size, when you heat up your assembly to kind of like assemble everything together, so at 600, 800 C or whatever, the polymers will actually evaporate, or you'll burn them off essentially. And so you're left with a pore size that is the dimension of the polymer that you selected. So you can target, let's say if you want 10 nanometer pores, you pick a polymer that is, the polymer chain length is going to be of that size. If you want bigger pores, you want 50 nanometer pores, 100 nanometer pores, then you pick longer chain polymers, maybe even branch polymers, but basically your polymer chain length is going to be longer. So then when that burns off, you get larger pores. So this is pretty typical for ceramic engineering, where you pick something sacrificial to template essentially. So that's what you do. Here, one of the examples I came across was you can just use starch. There's no need for fancy polymers as long as it's the size that you want. How you can put down that layer, very similarly, die pressing. So you just press the pellet that you want, or tape casting, or whatever. Very similar to what you did before, but now you're putting the cathode down first because it's going to be your structural component, right? And so then you put your electrolyte down. So the next layer down, same thing. You can disperse your ceramic electrolyte in some alcohol, spray it, dip coat it, what have you, screen print it. Then you put it in the furnace, heat it up. Now the two layers are stuck together. Then you do it again, put down your anode slurry. So what we talked about, the nickel oxide, which when you heat up in a reducing environment will become nickel. You'll reduce it in situ in YSZ. Same thing, you can deposit it however you want. You place it in the furnace again, and now you finish your composite, right? The assembly of all your composites. And so that's how you do that. Now you can also do it the other way, which is then you make your anode the structural component. So that's going to be the thickest. So you put down your anode first. So here you can see the anode being the thickest component. It's going to provide structural stability. Then you put your electrolyte on, and you want thinner the better, right? You don't want to have to use as much material. And then you put your cathode on similar way. So you just start from the anode, electrolyte, and then the cathode. Interestingly enough, this is what industry prefers, because it also it has this technique prevents a lot of cracking, delamination. The other thing is, if you use the cathode as your structural component, that means it's going to be the thickest component, the thickest part of your assembly. There's going to be a lot of ohmic resistance through the cathode. So industry tends to make the anode the thickest part of their assembly. Right. So, yes.
So I think you might have already said this, but I mean, why didn't we want to make our anode cathode like the thickest part besides just like structure? Or is there another reason?
No, that's it.
Oh,
Yeah, just for structural stability. Yeah. Because like the electrolyte, you can make it the thickest and make it the structural component, but you don't need to because your electrolyte just really has to conduct O2 minus and separate the cathode and the anode. So you just need your electrolyte to be as thick as it needs to be, like the minimum thickness where you're not likely to get cracking, but O2 minus will go through. So it's ionically permeable and it physically separates your two electrodes. Doesn't have to be any more than that. There doesn't necessarily have to be the structural component. Yes.
Is it supposed to be increases the oxygen mass transport resistance?
Yes, thank you. Thank you, thank you, thank you. Yes, that would make it a concern, not decrease. That would make it an advantage. If you decrease resistance, that is an advantage. Thank you. Yes. Right. Yes, okay. Sort of saying the same thing, but. Yep. Thank you for catching that. Okay, so I thought I'd wrap up this section on solid electrolyte fuel cells and talk about two examples of calculating how much hydrogen you need for light duty vehicles. This will be a launching point for us to talk about, back of the envelope type calculations to compare fuel cells for vehicles as compared to, what we have now, our current fleet. What's wrong with currently using gasoline fueled cars? Let's actually talk about the numbers. So we will do that. So this goes back to Olivia's question again, how big are these things and how much hydrogen do we really need? So if you're asked, okay, well, let's think about an electric motor. It uses 300 volts, it's a 300 volt electric motor. It uses 15 kilowatt of power. And let's say you're going to drive at 60 miles per hour, right? Because that's fuel efficient. And let's say the rated range for this fuel cell is 220 miles. Coincidentally, that is how far it is round trip for going from Columbus to Cincinnati. Okay. And let's say your fuel cell stack has 500 cells, right? That's pretty typical. So the question is, how much hydrogen in kilograms are you going to need to put in your vehicle? And what fraction of your vehicle's weight is that going to be? That's pretty important for, vehicle design. So we need first to calculate the current, right? So we have these numbers. So the current is power divided by voltage. So the 15 kilowatt power electric motor divided by its rated voltage gets us 50 amps. And that's the current that it's going to draw. Okay, so then we calculate, okay, well, how many moles of hydrogen do I need per time, right? I'm driving 60 miles an hour. So it's drawing 50 amps. And for a fuel cell, we're transporting 2 moles of hydrogen. We have 500 cells. So we divide 50 times 50 amps times 500 cells. So it's each of these cells is drawing, the stack is drawing 50 amps. And so we divide that by 2F, F being Faraday's constant. We convert 1 coulombs per second is 1 amp. So we get, this is how many moles of hydrogen are consumed per second. Okay. So what's that mass? Well, we just multiply by the molar mass. So if we're using 0.13 moles of hydrogen per second times its molecular weight, 2 grams per mole, we get, this is the rate of consumption, 0.26 grams of hydrogen for every second for this particular fuel cell stack. So then we say, okay, well, if I have to use 0.26 grams of hydrogen per second, and I'm traveling 60 miles an hour, and I'm driving 220 miles, that means I need my hydrogen source to last me 3.667 hours, or 3 2/3 of an hour. So that means, so we convert 3.667 hours to seconds, and you're consuming 0.26 grams of hydrogen per second. That means you need 3.432 kilograms of hydrogen on board if you want to make it from Columbus to Cincinnati and back at 60 miles an hour. And if you drive a little faster, you change that number. If you drive a little slower, you stop for food, you change that number. The amount of time that you need it for. You make a detour, you go sightseeing, what have you. You can change the number of hours that you're on the road. But so what does that really mean? When we're dealing with hydrogen, it's not just the weight of the hydrogen, as in like, oh, I need 3 kilograms of hydrogen, just pump it in, please. No, we need to consider the pressure of the tank itself. So typically, hydrogen tanks are stored at, let's say, 35 millipascal. That's the pressure that they're pressurized at, or they're compressed at. That means there are conversion tables. You just Google pressure, compressed hydrogen, how much can I store? So at 35 megapascal, you can store 23 kilograms per meters cube. So that means you'll need 0.14 meters cube, or convert it to cubic feet. So what does that really mean? That means you need this amount of volume for your hydrogen if you're going to pressurize your tank to 35 megapascal. A typical 4-door sedan is 110 cubic meters. Sorry, wow, that's a really big sedan. Cubic feet. So 4.9 cubic feet is about 5% of the volume of your vehicle. That's just now your fuel. Okay. So it's actually not that bad. And you can make it to Cincinnati and back. So not bad at all. Then the reverse engineering, the other side of the coin, the other question you can ask is, well, if I have the same rating, but now I have 5 kilograms of hydrogen, same electric motor. So you're going 60 miles an hour, you're using the same electric motor that's rated at 300 volt and draws 15 kilowatt of power, also still has 500 cells, but now let's say you have 5 kilograms of hydrogen, how far can you go? What's your range? So you do similar type of calculations where you calculate the current. So we already calculated that as 50 amps. We've already calculated that the number of moles of hydrogen consumed per second is 0.13. So that's the same converted to mass using multiplying by molecular weight, 0.26 grams of hydrogen per second consumed. But now we say, okay, well, if I have 5 kilograms of hydrogen and I use 0.26 grams of it per second, that means I will consume my fuel source in 5.34 hours. So a little bit over 5 hours. And if I'm going to drive 60 miles per hour, that means my range is about 320 miles. That's actually about the range of a gasoline vehicle, like a gasoline fueled sedan. So a few lectures ago, we said we couldn't make it to Cleveland. Now we can make it to Cleveland and back if we had 5 kilograms of hydrogen in our fuel cell vehicle. Okay, so yes, before I move on, yes, Dagny.
So, just like thinking about this,
Mhm. Mhm. Yeah. Mhm. Right. So right. So here it's right. It goes back to how efficient your engine is. So if you change your engine, you change exactly what you said. It's not taken into account, the efficiency of your engine is not taken into account the same way because the internal combustion engine is totally dependent on the combustion rate, right? So here, fuel cells, it's just, if you inject your hydrogen and, so it's different because the electrification is different than the internal combustion engine. So at lower temperatures, your fuel cell engine is going to be way more efficient. But when you go above 700 something degrees Celsius, your internal combustion engine will actually be more efficient. Okay, I mean, if you're burning gas at like 600-700 C, which you're not, but it is a totally different mechanism. So the efficiency of your engine is now going to be dictated by the fuel chemistry of your fuel cell, of your cell. I guess that's redundant. Okay, so let me pull up a figure that I think might be somewhat helpful to answer your question.
When you give it chemistry, you just mean like applying that hydrogen or oxygen.
Yes, I also, the mixing ratio, but also the temperature, like the reaction temperature of your fuel cell. And also the type of fuel. That's also what I mean by the chemistry. So you can input just pure hydrogen, like if you compress hydrogen, or more likely what typically happens is you input some sort of liquid fuel or some other fuel, like a hydrocarbon, like methane, say, and then you have an onboard reformer that will then convert it to hydrogen to go into your fuel cell. So you can change the chemistry. I will. One moment. Here we go. I'll just give you the punchline, Dagny, since you asked. So when you do a life cycle assessment, you'll see if your hydrogen fuel cell is more efficient than the internal combustion engine until 700 C. And then your engine will actually, your internal combustion engine will be more efficient. So I guess the answer to your question is yes, up until 700 C. And okay, let me just go back. And well, we will try to get through some discussions of life cycle assessment of fuel cells. Now, I should preface this discussion with there are many flavors of LCA. There are many models, there are economists, there are environmental engineers that work on perfecting these models. Well, improving, there's no perfect model, but improving these models, because what you'll see is we start to talk about equivalents that aren't like one-to-one comparison, which is why, asking Dagny's question, well, how do I determine if decreasing weight by using hydrogen, how does that equate to a gasoline? If I'm just trying to lightweight, then yes, hydrogen gas is much lighter than having a tank of gasoline. But are there other metrics that one can use to really quantitatively get to the answer of, is it worth it to replace our entire fleet of gasoline or diesel powered vehicles with hydrogen fuel cells? So that's what we're going to talk about next. Right. So people spend a lot of time thinking about this because whether we like it or not, and I think the fact that you're taking this class means this is something you look forward to, is that we focus on examples that pertain to light duty vehicles, is because it has some huge financial implications in the very near future. 10 years away is not at all is pretty close, right? And what we do now is going to have impact in, direct impact in 10 years time. So you could see here in the blue, the electric vehicle, fuel cell electric vehicle, but also electric, just, battery powered electric vehicle, that's going to be a dominant factor in, the types of cars that are going to be sold. And they're dictated by policies around the world, including, policies in the United States, where this is where the market is going. So I've highlighted, some decarbonization policies. So this is the policy I talked about earlier in the class, where a lot of the cars are going to, or if the bill in the European Union passes, that, all the cars are going to be electric, fuel cell electric or battery electric, what have you, but some flavor of electric. So that's happening, and it's happening all over the world, right? It's happening in the US, so switching to passenger electric vehicles, power generation in Latin America, also switching from going away, from gas and coal fired to some combination of natural gas, fuel oil, hydropower mixed in, with other renewable type technology like solar or wind. So the world is changing, but I don't think I really have to belabor the point to this audience anyway. But there's, reports and studies done on like what are the actual policies that are driving these changes. So not only in Europe, North America, but also Southeast Asia. So decreasing coal and oil, the Middle East. Well, actually, the Middle East oil is still dominant. So some things are not changing. And also the Pacific, hydrogen will also, hydrogen use will be increased. So that's all to say, there's a global convergence of going to renewable and such. So as we're replacing the technology that we have now, like gasoline or diesel powered vehicles, the typical recipe for assessing new technologies, the life cycle assessment, is it worth it to migrate our technology, consists of these 7 steps. Now, you'll see out there, when you read papers on life cycle assessment, there are many models, but they all sort of converge around these ideas of, okay, one, we need to analyze the materials, the raw materials, input and output, right? So if we have to get platinum or rhenium catalyst for polymer electrolyte membrane fuel cells, if we have to get gadolinium or cerium for electrolytes for solid oxide fuel cells, so on. So if you have to get cobalt, where are we going to get them from? And how efficient are they going to be? And where is the bottleneck going to be in the supply chain, right? So we talked about hydrogen for fuel cells, but if you're going to use methane, how are we going to collect that methane? How are we going to process that methane so that it's not full of sulfur and other gaseous impurities that will eventually kill your fuel cell and make it kind of a moot point, to even run your fuel cell. So we talk about raw material extraction. We talk about input and output. Then we have to quantify, like, how in the world are we going to compare apples and oranges? How do we compare gasoline and hydrogen? Like, what sort of method? Is it just thermal output? Is it just CO2 production? That's what we're going to talk about. Sorry?
Energy output.
Yep, and like how much energy goes in? Like, so if you have to compress that tank of hydrogen, where is that electricity coming from? Is it also coming from the coal and gas-fired power plants? The answer is yes, by the way. So it's not all zero carbon, okay? Net zero. Yeah, and then we'll also talk about, well, what's the most energy intensive part of this? Basically, once again, where is the bottleneck? Is it the pre-processing? Is it the cell itself? And then we'll talk about quantification of environmental impact, and then we'll compare the technology. So, our current system and then the new technology, and then we'll actually have to conclude, is it worth it? So I wrote down all these flavors as to our metrics as to how to compare. So you probably have heard of things like CO2 equivalent or carbon footprint. Quantitatively, what in the world does that mean? Okay, there's also discussions of like toxicity or how much water, you often hear like it takes X gallons of water to produce like one almond, right? So these are the types of comparisons that you would do to try to normalize the comparison so that everything becomes apples to apple comparison. Some of the other things that that go into a life cycle assessment are like particulate matter formation. So in the processing of your fuels, whatever refining method or processing method, you're going to produce particulates, as in like just carbon that will be emitted into the air, soot, what have you. But these particulates, if they're of a large size enough, they will matter because they will start absorbing infrared light at a significant rate that will contribute to global warming, right? So to the greenhouse gas effect. So what people talk about is, how many kilograms of particulate matter 10 equivalent. So that's 10 micron equivalent. So is the particle, at least 10 micron size, in which case then we start caring about it. Or is it smaller than 10 micron? Right. And then also these are things like 1,4-dichlorobenzene equivalent, oxidant, volatile compound that get formed. So there are different ways of talking about equivalents. We'll talk mainly about CO2 equivalent, so CO2e, as it's referred to, and also particulate matter formation in our discussion of LCA. Oh, my, okay, we are 1 minute over, so we will pick up here on analyzing the relevant energy input and output of hydrogen into fuel cells. Okay. Next time.
So is cost just, I guess,